Welcome everyone. I am here to understand the topic that I I am going to give a demonstration on the control of engineering state space analysis. So in this topic we will see the various types of state space representation and its uses from the control point of view, also from the student's learning point of view. So we begin our topic. So state space model is any kind of control system model which comprises of mainly three parameters. And these parameters are input, output, and the states of the system. So state variables are generally represented in x1 to xn. Outputs are y1 to y2, and input variables are q1 to q1. The dimension of the input vector, output vector, and state vector all could be different. So moving on, the general representation can be understood with the help of an example. So first of all, we have taken a card example in which force is being applied on stationary vector, and we have to measure its outputs. So for the state point of view, we have taken t, which is the displacement, t, which is the velocity. For the input, we have taken force F, and output is again taken as the displacement, which is x. So if we write down the equation of motion, we can obtain this dv by dt equals to acceleration, which is force divided by mass. And after solving for vt with a definite integral from t equals to 0 to t, we will find that vt is equals to vt naught, which is the initial velocity, plus 1 by m integration over ft, which is the integration of the acceleration over the time. And the similar way, when we proceed for finding out the xt, which is the displacement in this case, so we obtain this equation here. So state of a dynamic system is generally represented with a minimum number of variables which could help you to understand the behavior of the system over the time. So if we can correctly acquire the knowledge of states at t equals to 0, then we can predict the system behavior for all time t, which is greater than t naught, and generally the state space representation will be obtained with the help of first order differential equation. So what is state model? State model representation is like a mixture of two equations, state equation and output equation. State equation will be a first order derivative equation, which is term equals to x plus du, and the output is y equals to x plus d. So this matrix A is a state transition matrix which relates the derivative of the states with the state itself. The matrix B is input matrix, input gain matrix, which relates the derivative of the states with some given input. At the same time, the y is, which is the output, directly related on x with a constant matrix C, which is called output gain matrix, and it also depends on this input applied. So these terminologies are represented in this manner. Now we will take one example of this state space representation with the help of an electrical circuit which is given here. So we can see in this electrical circuit we have two loops. Loop 1 which comprises of source E, resistance R1, inductance L1 and capacitor. The loop 2 comprises of capacitor C, inductor load L2 and resistive load R2. So we are expecting two equations for this which will be obtained using Kirchhoff's voltage law. At the same time, as we have learned from the definition that the minimum number of changing variable could be represented as a state. So we can see here the capacitor C has V voltage across it. So we all know from the property of capacitor and inductor that in a transition phase when we apply the voltage, sudden change of voltage does not occur across the capacitor. In the similar way, sudden change of current does not occur across the inductor. So it takes some time to develop the full voltage across the capacitor and to flow the full current across the inductor L. So this is the transition time in which we have to define all three variables in terms of states. So we have defined here state x1 as voltage V, which is voltage across capacitor C, state x2 as current across inductor L1 and state x3 as current across inductor L2. Next we will obtain the equations for Kirchhoff's voltage law and these will be the equations accordingly. So we can see here that the dynamic equation 1 reveals the rate of change of voltage V across this capacitor C is equal to the division of capacitance C across both of these uh, two currents I1 and I2. Similarly, when we apply equation into loop 1, we can obtain this closed equation, closed loop equation L1 di1 by dt plus R1 I1 plus E minus V equals to 0, and when we short it out, we obtain this form. And for the loop 2, we can have this relation as well. So equation 2 and 3 are quite similar, which are obtained with the help of KVL. And the first equation is very much equivalent to the KC, which is the Kirchhoff's current. Now, how do we represent these equations in the state space equation? Is that by taking our assumption x1 as B, x2 as I, and x3 as I2. x2 as I1 and x3 as I2. So when we do this, we can obtain this right side of the equation where we have this set dx1 by dt equals to x1 tau. This one tau is represented equivalent for the first order derivative of the state x1. And in a similar manner, we can obtain for dx2, dx3 corresponding for the variable b, I1 and I2. After sorting everything out, we can obtain this relationship amongst the state variables, and this matrix will be here A, which is the state transition matrix, and this will be the matrix B, which is the input gain matrix. And it depends on us what we want to obtain as our output. So here we can see we have selected two outputs. One output is the voltage across resistance R2 and another output is the current I2. So when we put these into this equation, you can clearly see that only state x3 will be responsible for these two outputs and state x3 is I2. In a similar fashion, we can go for another example. Here we have taken this electrical circuit. Now we can clearly see here that we have two capacitors. That means there will be two variable voltages, and we can obtain the equations accordingly. So let us define our states first. We have defined our states as V1 equals to x1 and V2 equals to x2. The input is this supply voltage V and the output is Y, which is the current flowing through the capacitor C2 via resistance R2. The dynamic equations can be obtained accordingly. Here we can see these two dynamic equations. This is for the state V1, this is for the state V2, and after separating out the variables, we can see that first equation is depending on the input voltage V, which can be observed from this first group, and the second equation is not depending on the source voltage, and this can be seen through this equation. So moving on, when we separate our variables as x1 and x2, we can see that we have obtained these two state equations, and after separating it, we can obtain the state transition matrix A, the input gain matrix B, and for our output, we can have this relation y equals to I, which is V1 minus V2 by R2, and then this V1 and V2 will be for the states. So this C matrix will be exactly like this. We can have another example, which is the example from electromechanical system, in which we have taken an armature controlled DC motor, and this equation, the equation for this purpose will be electrical and mechanical. So we will see them one by one. First of all, let's look at the electrical part of the equation. So this is input voltage EA, which is equal to the voltage across this inductor, which is represented by L divided by dt, plus the voltage across this resistance RAIA, plus EB. EB here is the back EMF which is produced in the armature coil due to the rotation of this shaft. So we can obtain this relation here. EB equals to kp d theta by dt, generally known as angular rotation speed, and represented by omega. Second equation here, from the electrical side, we have Tm, which is the motor torque, equals to Kp, the torque constant, multiplied by the armature current. And that is why we call it the armature controlled DC motor, because the torque here can be obtained by varying this input voltage EA in the armature, and there is another different kind of arrangement for the motor, but for now we are seeing this armature control. Looking at the shaft dynamics, we can see here J d theta 2 by dt square plus f d theta by dt equals to the torque. F J is the inertia of the shaft, F is the coefficient of viscous friction. So the net torque here will be the product of the coefficient of viscous friction multiplied by the angular speed, and this will be equal to the net torque, and this net torque is obtained via this equation, which is a direct dependent on current IA, and the IA is produced by the first equation. So we can see here that applying the electrical voltage, first it converts into current, and then this current is converted into the torque, and that torque produces the rotation into the shaft, and we can obtain theta d theta by dt and d square theta by dt square. So for state variables, we have selected x1 as theta, x2 as theta dot, and x3 as the armature current. Then we can see from this mechanical equation, we can have this relation x2 dot equals to f by j x2, which is a negative quantity, minus kt by j x3. And from this electrical equation, we can obtain here x3 dot. This is for the I dot. So dIA by dt is represented as x3 dot, and then this part in the right hand side. So after sorting everything out, we can see that in the first state equation, which is the x1 dot equals to x2, just a simple relationship between state variable theta and theta dot. So here x1 dot equals to x2. If we split it into matrix product, we can see that x1 dot equals to x2. And next, these two equations are often from mechanical and electrical part of the equation. The input matrix, which is 0 0 1 by LA, is again only will be contributing to the electrical part, because remember we have said that in this electromechanical system the input is provided in terms of voltage and outputs are obtained as the actual physical angular displacement velocity. So accordingly the output equation can be obtained here for x1, which is the theta, given by this C output gain matrix multiplied by the state matrix, and the overall state equations plus output equation will be represented in a state model, and that is shown here with each set of equations. Now we will take another example of an electromechanical system in which there is string fully attached system to the shaft of the motor, and we will define our states accordingly from this figure. State x1 is the current Ia1, x2 is theta, x3 is theta dot, x4 is the displacement caused into this mass which is attached to the string, and x5 is the rate of change displacement in this direction of the force. So our output will be the displacement measurement, which is the displacement of the mass, and the input will be again here the voltage. So we can relate this system to some kind of weight lifting mechanism via motor. So when we write the dynamic equations, then we can see here again with the help of this back EMF, this motor part of the equation will remain same as in our previous case, and this torque which is getting transferred to the pulley from the shaft of the motor, that will be given by J d2 theta by dt square, and again this torque is obtained by the current produced in the motor armature. So we can see that there is a direct relationship between this inertia of this pulley, which is J d2 theta by dt square, and this is equivalent to this kti. So the torque due to inertia is equal to torque produced by the motor, and from that we can connect this to the linear motion of this block of mass m, which is F equals to m d2x by dt square. We are not considering any stiffness constant and friction coefficient here, so that can be directly related to this force equation, and the torque will be equivalent to force multiplied by the radius of this pulley shaft. So the whole equation gets converted into ETIA equals to m times radius r times d theta by dt. So when we have to obtain the state equation from the first equation of the model, we can obtain our state variable x1 dot, which is the IA derivative, and this will be the equation. x2 dot equals to x3 because this is again x2 is theta dot, this is, and this is x3 is theta dot. So x2 is theta, x3 is theta dot, so these two are equal, and this current equation will give us this variable derivative of x3, which is the theta dot derivative, that is the theta double dot, which is d to theta by dt square equals to kt times j, and that will be equivalent to x1. x1 is the current, and accordingly we can obtain this x4 dot equals to x5 for this displacement and velocity, where x5 is x dot and x4 is x. So x dot equals to x dot, and x5 dot, which is equals to x double dot, is represented here that d to x by dt square equals to kt upon mr times I. So IA is what? State x1. So we can obtain this uh, derivative of the states, how they are related to the state themselves, and then from this relation, after separating the variables x1 to x5 from the constants, we can obtain a matrix. So this is the A matrix, which is a state transition matrix here, and this is the state derivative, and this is the state themselves, and this is the input matrix B. So we can easily obtain this model for any electrical, mechanical, or electromechanical system. Next, we move to the topic of transition of one form of transfer function to another form. For that, we have to use some assumption. So this transfer function Ts is given in terms of Ys upon Us. So Y is the output of the transfer function of the system, and U is the input to the system, and these are represented with the help of the numerator and denominator. So these are constants b1, b2, b3, and bn in the numerator, and the denominator coefficients are a1 to an. So we need to split this Ts equals to Ys upon Us into some intermediate variable so that we can introduce a concept of state here. For doing that, we will just split it. Ys by Us equals to x's by us times ys by x's. So when this x's and x's gets cancelled, ultimately we obtain ys by us. So now we will separate the numerator and denominator with the product of these two terms. So we separate x's by us first term with the 1 upon this denominator term, and ys by x's to this numerator term. So now we need to solve for this term first, and we can obtain that state model for x by us as x by us equals to 1 upon this polynomial of s, and when we multiply both sides, then we can obtain u equal to x's times multiple of these variables. So s to the power n, a1 is to the power n minus 1. So we know that a multiple of s in any variable means we have that much order of that variable in time domain. So right now this xs gets multiplied by s to the power n. This means that we are looking at the nth derivative of the x. So this x n does not mean x to the power n. It means that nth time derivative of x. So accordingly, we multiply these x's to each and every term, and we can obtain this relationship in which we can see that by the law of differential, we have n number of state variables. Now we will separate these variables one after another. So here we can see we have taken state x1 as x, x2 as x dot. So what is x dot? X dot means x1 dot. So this x2 equals to x1 dot, x2 dot equals to x3, x3 dot equals to x4, and accordingly xn minus 1 dot is equal to xn. So these are the assumption for the variables, and for we have to obtain this xn dot, then we can do this. So xn dot equals to, as I have told you, xn dot means the nth derivative of that variable x, and then this means this entire equation which is representing the n number of states, so that will be for the final xn dot. So now when we rearrange this, like moving left hand side to the right hand side, the right hand side to the left hand side, we have x1 dot equals to x2, x2 dot equals to x3, and accordingly xn dot equals to. Moving on, when we separate our variables from their derivative to constants, we can obtain that this is the form that we finally get. This can again be represented in the state equation, which is x dot equals to x plus d. Now we need to find out for the outputs. So ys by x is equal to this polynomial, and when we multiply both sides, we can obtain y equals to d1 x to the derivative n minus 1 to dn times x. So considering x1 as x, we can now see again the same assumptions hold here, and then we can see that this y is nothing but simply the product of bn to bn by this x1 to xn variable. So this is the general procedure for obtaining a state model from the transfer function. Now we can take one example here and see. First we have separated these new state variables, this is y and y is y axis, and then we can separate with 1 upon this polynomial of s, and this polynomial y is equals to this numerator of the transform. Then we can obtain directly the state model which was earlier obtained in the exam, in the demonstration for this conversion, and this is for the output. So you can go back and look into the earlier explanation, and you can directly relate it to the denominator coefficients here, which is so dot equals to minus 4 times x1, minus 3 times x2, minus 2 times x3, and minus 1 times x4 plus q. And from the above we can see x1 dot will be equals to 0 multiplied by x1 nothing, and the only thing remains here is x2. x2 dot will be x3, and x3 dot will be 0 0 0 and x4. And accordingly for the output from the numerator we can see y equals to 2 times x1 plus 3 times x2 plus 4 times x3 and 5 times x2. Now we have to understand one important topic for this state space expansion, which is the partial fraction method. So for a given transfer function, for example, we have taken here 2s square plus 6s plus 2 divided by s plus 1 s plus 2 s plus 3. So we have to separate these in the form where each part is solvable with the help of inverse Laplace equation. So if we are able to successfully do that, then we can obtain something like a upon s plus 1 plus b upon s plus 2 plus c upon s plus 3, and then you take Laplace inverse and have first term a e to the power minus 1t and b e to the power minus 2t plus c e to the power minus 3t. So to solve this, we apply simple partial fraction method, and we can have a denominator and numerator. And we can see in numerator we have s square multiplied by a plus b plus c, s multiplied by 5a plus 4b plus 3c, and this last term is 6a plus 3b plus 2c. And the denominator is again s plus 1, s plus 2, s plus 3. So if these two polynomials and transfer functions are equal to each other, then the coefficients of s square will be equal to a plus b plus c equivalent to 2. The coefficient of s, which is 5a plus 4a plus 3c here, will be equivalent to 6, and the coefficient of this constant term, which you can say is to the power 0, is 2, which is equal to 6a plus 3b plus 2c. So when you solve this, you can obtain a equals to minus 1, b equals to 2, and c equals to 1. And then using this partial fraction method, we have successfully separated our terms, which is minus 1 by s plus 1 plus 2 by s plus 2 plus 1 by s plus 3. We can have another example here, and after solving this, this in fact this is the same example, and we are solving it with a different method. So what we are doing is that we have written it a upon s plus 1 plus b by s plus 2 plus c by s plus 3, and first of all we are obtaining for the solution of s plus 1. So we have to put s equals to minus 1, which is s plus 1 equals to 0, and then when we put here multiply s plus 1 to the whole equation, then we can obtain a equals to minus 1. We repeat similar procedure for b and c, and we can obtain this b equals to 2. So for finding b, what we have to do, we have to multiply this whole transfer function with s plus 2. So we have done here s plus 2, and then we have put s equals to minus 2 in this part, and we have obtained b, and accordingly we can obtain c, and this will be the same answer which we have obtained earlier. You can pause and go back to see the answer. So with the same equation, we can proceed for a little bit complicated case here, which is again a divided by s plus 1 whole square plus b by s plus 1 plus c by s plus 2, and this is generally we are expecting. So for finding a, what we need to do, we need to multiply the entire transfer function with s plus 1 to the power 2, which is s plus 1 whole square. Take this derivative first, and then put x equals to minus 1. So by doing so, we can obtain a equals to minus 4. For b, we have to simply multiply this by s plus 1 to the power 2, which is plus 1 whole square, and put x equals to minus 1. Then we can obtain b equals to 10. And for c, it is very simple. You have to just multiply with s plus 2, which we have done here. and then put s equals to minus 2, we can obtain c equals to minus 10. So the final partial fraction for 6s plus 2 divided by s plus 1 whole square s plus 2 equals to minus 4 by s plus 1 whole square plus 10 by s plus 1 minus 10 by s plus 2. So why we have done that? We have done that to obtain another form of transformation from transfer function model to state space model, and that is called the canonical form. So this canonical form is important from the designer point of view when you are given a task to design a certain control system. So let's see how we can obtain this canonical form. So we have here s cube plus 8s square plus 17s plus 8 divided by s cube plus 6s square plus 11s plus 6. This is the transfer function that we have here. And by doing some calculation, we can separate this 1 plus this part. So after separating, we can take the common factors in the denominator, and which will be s plus 1 times s plus 2 plus s plus 3. So when we obtain ys by us equal to in this form, in the later term will be split in three terms, which is obtained with the help of partial fraction method. So finally we can write ys equals to 1 multiplied by us plus minus 1 by s plus 1 times us plus 2 upon s plus 2 times us plus 1 by s plus 3 times us. And then from this we can obtain our block diagram, and you can see here this is ys, which is the sum of four incoming signal, in which the one signal which is directly coming from us. So this is the first term. Second term is coming with the minus 1 gain and 1 by s plus 1 transfer function block. So whatever is the middle of these two, the gain block and this transfer function, which is a first order derivative model, first order state equation, first order transfer function equation, we can say the middle portion will be the states. So accordingly we will have state x1, x2 and x3, and by doing some calculation we can separate these states and relate with the input. So let us first we do this calculation for the second term, which is minus 1 by s plus 1 times us. So by separating we can have s x1s plus x1s equals to s. So s x1s is x1 derivative. So we can have this first relation of the states. Accordingly, when we solve the second term, we can have this second equation and the third equation. And when we read all these three equations, we can have this state space uh, equation, which is x1, x2, x3 dots, and this is the canonical form, in which we can see we have only this diagonal term remaining here, minus 1, minus 2, minus 3, and these are this is the state transition matrix multiplied by this state, and now we can see the input u is contributing to each of the state derivative. So this is another form, and for output we can see these states here x1, x2 and x3 are directly multiplied with these three constant minus 1, 2 and 1. So we can have this equation here, and for input we have this. So this is the d. D is some simply constant which is having value. So this was final result. Now we can see some other example for this canonical form, in which we have taken this transfer function This is 2s square plus 6s plus 7 divided by s plus 1 whole square times s plus 2. And when we do this partial fraction method, when we apply, we can obtain these three separate terms, and this will be the corresponding block diagram. So we need to understand this block diagram. So first of all, look at the first term, which is 1 by s plus 1 times minus 1, and this will be our state x1. So we can see here y is there, and the one term which is contributing 1 by s plus 1 times minus 1, which is going to summing point for y. After that, we have another term which is s plus 1 whole square. So is s plus 1, 1 upon s plus 1 whole square is directly multiplied by u. But when we look from this place, it is showing 1 upon s plus 1 whole square. So this will be x2, and later on the constant 3, which is represented as a block here. So this will be state x2. It will take little bit of practice to convert into this form, and you can always pause the slide and have a look and try to understand. And the last term is here 3 upon s plus 2. So u times 1 upon s plus 2 times 3. So the middle term between the first order transfer function and the constant will be the state. So this is x3. So again we can see here that we have obtained for the first term this transfer function x1s by us equals to 1 upon s plus 1. By separating these variables, we have x1 dot equals to minus 1 x1 plus u. Similarly, we can do for the second term, and similarly we can do this for the third term. So finally, when we do this separation and we obtain our state equations like 1, 2 and 3, and put this here, and we can have this form of equation here, in which now we don't have this diagonal matrix, and this is having a special name which is called this Jordan block. So Jordan block is a sub block in the canonical form of this state space representation, and generally this type of state space representation is called Jordan canonical. This will be the output equation for these three constants minus 1, 3 and 3, which are multiplied by x1, x2 and x3 respectively. This is the state space model. The final topic which remains is the conversion of state space model to a transfer function model. So as we know, we have this state space model x1 x dot equals to x plus b, y equals to cx plus d. Then we take the Laplace transform of the first equation, and we have sxs plus axs plus b equal to, and then we can separate this input and state. By rearranging, we obtain this xs times si minus a equals to bus. Then we can see that the state xs is directly related to input us with si minus a inverse times b. Similar thing we can do for the output y, and you can see here when we take the Laplace transform of y, we have ys equals to c times xs plus tus. And one thing, this I here which is multiplied by s is the identity matrix, which is a diagonal matrix, which all the diagonal elements are value unity. So when we put this xs here, we can obtain the equation for y, which is equal to c times of xs. So xs is si minus a inverse b times us, which is placed here plus T, and by separating we can directly obtain the transfer function ys upon us equals to c times si minus a inverse b plus g. So for example, we take this state equation here in which x dot equals to ax plus b and y equals to cx and b is taken as 0. So we have to apply this equation c times si minus a inverse b plus g and we will obtain ys by us. So first we obtain si minus a. So this is s multiplied by this identity matrix minus times this state transition matrix A and we obtain this matrix A. Then for obtaining the inverse, first we find the adjoint and then we divide it with the determinant. So for finding the adjoint we have this formula where adjoint is obtained by taking the determinant of the remaining elements, and for that element if we are considering C11 then we have to take the determinant of B, C22, C32, C23 and C33. So if we are taking C11 means we are considering S, and this column and this column will be uh, eliminated and we take the determinant here. So if we take the determinant we will obtain s square plus 3s plus 2, and similar procedure can be followed for all the remaining elements to obtain the adjoint matrices. So after taking the adjoint matrices and finding all these coefficients, that is from C11 to C33, we have to find the determinant, and the determinant of this Si minus A is equals to Sq plus 3s square plus 2s plus 1, that we can obtain by using the formula of determinant. Then we can have this Si minus A inverse equals to this form, which is the adjoint matrix divided by the determinant, and the transfer function Ts can be obtained as C, which is 100, multiplied by this Si minus A inverse multiplied by B divided by this part, which is the determinant of Si minus A, and plus T. So finally we can obtain the transfer function as, after taking multiplication and multiplying, this is 10 times s square plus 3s plus 2 divided by s cube plus 3s square plus 2s plus 1. Another example for this conversion from state space to transfer function, we have taken here this MIMO system, which is a multiple input and multiple output system. As the name suggests, we can see here we have two inputs, U1 and U2, and two outputs, Y1 and Y2. We will have to follow the similar procedure for finding of the transfer function. We just need to find Si minus A inverse, and then we can find this Tx equals to C times Si minus A inverse B plus T divided by this matrix. So now we can see that the transfer function is a matrix, not a, not a polynomial form that we use to obtain for the single output, single input, single output system. So this matrix suggests that we will have the relationship between y1 and y2, u1 and u2, of this transfer function matrix. So I would suggest to go back into the video. If you have any confusion regarding any slide, slow down, think a bit, and then you can obtain clear out doubt. For any more clarification, you can comment me in this comment box, and then I'm sure I will be able to help you out with your doubts. Thank you for watching. We will see you soon in the next video.